Okay. All right, so the last time we talked, we went over some interesting concepts, I think, primarily because you guys have probably seen these concepts almost every day of your lives, and you may or may not have realized the sensors that you're actually dealing with, right? So now we're peeking under the hood a little bit. When we talk about a humidity sensor, temperature sensor, pressure sensor, whatever, what does that mean? What is it? How does it work? That is a little bit of what we delved into the other day. Again, the general term, the industry standard is transducer, typically. Okay, the transduction is turning one physical property into another. Okay, the physical property of interest to us is electricity, right? Typically the amount of voltage, or it can be the amount of current, or some gas sensors are like literally the number of electrons leaving the electrode is proportional to our signal. Okay, crazy stuff like that. All we're saying is that we have a property of interest. We are doing some clever chemistry or mechanics or chemistry to it in order to create a relevant and useful device, right? This device has to talk to our PLC somehow, right? That's once we actually create the transducer, that information is still within the metal can of the sensor, right? We have to get it out and into the world to make it useful. So then the question becomes, how do we do that? The answer of which was, several different ways, but this starts to get into communication protocols. Okay, again, generic terminology that is helpful for you guys to know and possibly research in the future is communication protocol. Okay, I2C or I2C is a communication protocol. Same with SPI, SPI bus, UART, right? All these different kinds of data communication protocols is just one way to get data information out of our sensor and into our computer or cloud or whatever, right? So it's actionable and useful to us. So, like I said before, for electricity, there are a few properties that we can measure. We already went over voltage, we already went over current, we went over capacitance a little bit, kind of like to the extent that I want to in this course. Again, this is like Physics 3, like getting into it a little bit, not necessarily exceptionally relevant for programmable logic controllers, but knowing like what a capacitive sensor is and how you might see that in industry as a flow sensor or a touch sensor or whatever, okay, really useful, right? The idea of capacitive sensor or an inductive sensor, and knowing that an inductive sensor is probably going to do one thing and a reed switch is going to do another in one situation, right? All good vocabulary. Okay, so one thing that we didn't go into last time is inductive sensors. Okay, I just gave a little bit of a hint there. But my favorite example of an inductive sensor is the type that recognizes your car is rolling up to a stoplight. Okay, so people may or may not know this, but you see that almost like a chunk is cut into the ground right before you roll up to that sign. So what's actually embedded in the earth or in the ground is a very large coil, literally a large coil that is run underneath the cement pad, and there's always some current running through it, right? There's an inductance in this coil, okay? When you park a big block of metal over it, like a big motor or a motorcycle or whatever, okay, it couples, the magnetic field couples between those two pieces of metal, the coil being one piece of metal and the motor or whatever being another. Okay, and then the system can sense this disturbance. This link, the amount of mutual inductance, it's called, changes. Okay, so we're sensing inductance. If there's more inductance or less inductance, it's the presence of a large piece of metal, and then it can, do whatever with that. So the PLCs that live in the box next to the stoplight will register that inductive sensor and then do something with it. It's wired into the input of a PLC somewhere in that cabinet, right? Inductive sensor meets PLC. And that's where the rubber meets the road here in this particular case. Any questions about inductive or capacitive sensing? All right, so again, preview. I would love if you guys turn these into flashcards or something for yourselves. Okay, make sure you know these terms. They're not complex by any means, but like knowing what a reed switch is, knowing what a limit switch is, knowing this by sight, right? If I show you what is this, you go say that's a limit switch, or that's a what do they call it? Limit switch, or I'm blanking. I'm sorry. Then this is knowing how a button works, right? That we're bridging metal, or just deflecting this piece of metal that is bridging these two contacts, or this contact and these contacts. We went through light-dependent resistors, mercury switches, A and B encoders, rotary encoders, potentiometers, float switches, all that good stuff. I don't feel like we have to go over that. It's still worth mentioning, going back over the difference between thermistors and thermocouples. Okay, so just to explain it one more time, really drive the concept home. Okay, thermocouples work by using dissimilar metals that are wound together, just like this. Okay, literally two wires. We terminate this one this way, we terminate this one this way, and if you measured these with a multimeter, again, just bare wires with a bare multimeter, you will find, you know, plus V, minus V. If you look between these two probes, I think it was like 0.7 microvolts or something like that. Okay, just like as it is. If you take a flame to it, you might get, you know, like 70 microvolts, or 7 microvolts and 70 microvolts. Okay, and then the difference between 7 and 70 is 1200 degrees. Then you can use that as a temperature sensor from anywhere between room temperature and 1200 degrees, right? Issue is that this voltage, 70 millivolts, is very, very small. Okay, 5 volts is 5,000 millivolts, right? So that's kind of the more traditional range we're used to measuring these things. So we need an amplifier. We need a device that sits in between. Do I have it? Okay, this is good. We need a device that sits in between our PLC and our raw metal junction that boosts the signal, that amplifies our signal without blowing up the noise. And then, so that's a little device that would sit right next to our box, just on our rail like so, that you would plug the probe into, and that will go into our PLC in order to monitor it. Okay. Thermistors are different. Okay, so thermistors, back. So thermistors are like, they're inside of 3D printer heads. They're inside of a lot of things that need really fast, relatively low temperature heating monitoring, right? Like 200 degrees Celsius-ish. Much above that is like a little bit too high. Okay, but for like an oven, you probably want a thermocouple, right? Again, like 500 degrees rather than 200 degrees. Okay, but a thermistor is essentially just, that's dead, a resistor that, a good resistor doesn't change resistance with temperature, right? It's more or less stable. A resistor in Hawaii is the same resistance as it is in Alaska, right? A thermistor is made bad on purpose so that it does change resistance with temperature. It does so in a very controlled and understood way, so that when we know that when this resistance changes by a kilo ohm, you know, we have changed by so many degrees, okay? But our systems don't work in kilo ohms, right? We can't really measure resistance directly. We have to turn that into something we can measure, current or voltage, right? And that, again, takes a little box that you plug your thermistor into, or create this bridge like I showed you here. It does essentially the same thing. Okay, this is getting, again, you know, kind of into the weeds, the circuitry of it all for electrical engineers and such. But if you guys understand this, with our voltage divider here, we can get voltage from our resistance, right? This is a voltage divider, a potential divider, that if this voltage is so high and this voltage is stable, this one goes up or this one goes down, this voltage will go up and down as well in an efficient and measurable and repeatable way. Okay, nice and simple, and literally 2 resistors, 2 jelly bean parts, and a thermocouple could plug right into a PLC. You actually don't need a box beyond these 2 resistors for that. Or you could have something fancier that, you know, has its own sensing in it that digitizes the signal and presents that digitized signal to the PLC instead. Right? Another option. We went over accelerometers. Again, this is just like nice to know entry to the world of MEMS devices, MEMS, right? Essentially printed sensing devices, okay? The idea of like what does an accelerometer sense, okay? Angulation, absolute angulation with respect to gravity is what an accelerometer senses, okay? It also will do force as well, right? Not just gravity. If I exact force to make a accelerometer move that direction, it will register that force, right? Because we have a weight that is more or less suspended in three-dimensional space, right? That whenever we bump that weight, we can see how that moves, right? And how fast it moves and how much it moves. The gyroscope only measures change, right? So if I hold the gyroscope still for a little bit, it won't actually register any change. If I torque it, it will give that change, right? That change in angular momentum that occurred. And then if I leave it still for a while, it won't register a change. Okay, so gyroscopes all around angular changes. If you put a accelerometer, a gyroscope, and a magnetometer together, a magnetometer actually registers the Earth's field, okay? And you do actually some really high-level math. It's called sensor fusion. It uses artificial intelligence and machine learning these days, right on the chip. But essentially, it uses these three data sources: accelerometry, gyroscope, and magnetometer for each of these axes. Okay, so this is a 9-axis sensor to understand exactly where an object is and how it moves throughout the world. Okay, again, like VR equipment uses this. Factory robotics uses this. You know, when you really want to make sure or track something through space, an IMU is the way to go, right? Missiles use this, all that good stuff. Okay. We also brought up the idea and the flexibility of a pressure sensor, particularly a differential pressure sensor. Okay. So a lot of people who aren't in the industry, you know, I keep seeing in the industry, but if you're using a PLC in an industrial environment, you're probably measuring something. Okay, if you're measuring flow or pressure or volume or weight or mass, right, whatever. Pressure sensors have a home in almost all of those places, right? To measure weight, you use a pressure sensor. To measure flow, I'll show you that again in a second, how we can do that. All the way to, you know, the literal pressure inside of a canister. Okay. The design of that pressure sensor and the use of that pressure sensor and which one to use is often up to the person who is set to task, right? So someone might say, you know, we have a pipe. We have an existing PLC system that's on a rack, right? Our PLCs live in here. It's got some free ports on it on the top that we can plug into. We have a pipe that's got whatever flowing through it. Could be water, could be sludge. Okay. And they have a desire to know what's going on in that pipe to get that into their PLC system. Okay. Quite often that would be like the literal task that you would be set to task with. How do we measure this thing? Then you would know to look up flow sensors. You know, you could possibly find one that uses a differential pressure sensor. You would want to understand if you want to have like a pinwheel flow meter, for example, something that is in the flow of your water or isn't. Okay. All of these things are very useful to know. That's kind of what I can add. All right, so a couple of good ones to know for pressure sensors can essentially be illustrated just like so. Okay. Each of these has a membrane. Okay. You can think of it like a little balloon membrane. Okay. This side often has a port that is exposed to a hose, you know, that we can put wherever we want. I'm just going to draw like that. Okay. And the other side is kind of the differing factor depending on the design, okay? Sometimes it has a sealed reference gas, some pressure that we always want to compare against. You know, absolute vacuum, ambient pressure, whatever. If we're at the bottom of the ocean or in space, this reference volume would always give us the same pressure. It's only what are we comparing that pressure to? And that pressure will cause this membrane to bulge out or bulge in accordingly. Okay, you guys see that if this bulges out, this means that this pressure is greater than this pressure. So we have a negative pressure on our inlet. Same thing for the positive, right? We would get a positive deflection of our membrane, okay? This membrane right here could be made of different technologies, but it could be capacitive, it could be strain gauge, okay? Again, more transduction types. Getting a little into the weeds of the design of the sensor, but this is a absolute. Let me check my math here. Absolute, got it. Okay, with a reference volume inside of it. Okay, it's placed there in the factory, right? Factory settings have it be whatever it wants. Sometimes it's filled with argon, whatever. Then we have the open vent. Okay. This is always comparing against the environment of the sensor. Okay, wherever this tube is might be somewhere really specific, like on the inside of an instrument or on like the exhaust of a car, right? We're sampling it from somewhere. But it's important to us that we always compare the pressure of that sample against the pressure of air. You do this because you instantly get rid of a lot of errors that way. Okay, is if the weather's like particularly high that day, or you're on a mountain or whatever, having this little port here for sampling the ambient air instantly gets rid of that background noise. Okay, you're always sampling kind of like what you want to sample, if indeed this is the sensor that you want to use. Okay, so this is often called open vent or ambient reference. Okay, this one is probably my favorite because it's the most flexible. You can use it in any of these conditions, depending on where you place this other port. But here we have the differential sensor. Okay, so you guys see here that I could make a differential pressure sensor into an absolute pressure sensor if I wanted to, by like having a volume of no pressure here, right? Or I could make it an open vent by just exposing it to air, or I could make it a true differential by plugging this other hose into something. Okay, what we talked about before was called a Venturi type flow meter. They often have this weird crosshair in the middle of the tube. Okay, and this crosshair can be really, really thin, but it's just enough to disrupt the airflow. Okay, so airflow comes in through here nice and straight, and then it kind of gets disrupted just a little bit. That's enough that the pressure on this side of the tube is just a little bit greater than the pressure on this side of the tube. It's called the Venturi effect. Okay, you could achieve the same thing by reducing the diameter of the tube. Okay, but cool thing is if you monitor the differential, right, the change in pressure from one side of that feature to the other, that change in pressure is equal to the change in flow. So you now have a flow meter using a pressure sensor, right? Entirely just how you hooked it up and how you program the system could get an exceptionally accurate and amazing non-contact, right? We don't have a pinwheel in the middle of our sludge getting clogged or whatever, okay? It's one potential solution to the problem. There are also many. Just one other flow sensor type, just while I'm thinking about it, is ultrasonic, okay? If you have a sending head right here and a receiving head right here, okay? This is like an electric probe, this is an electric probe. Both of these plug into a PLC or a box that plugs into our PLC. Turns out that the Doppler effect has an effect on the flow rate, okay? That these ultrasonic sensors, this is an ultrasonic flow sensor, okay, that essentially digitize for us the flow rate and just report it over an easy to read interface. Okay. So that's a good point to whip back, is that all of these sensors, flow sensor, pressure sensor, ultrasonic sensor, right, they might give us the exact same parameter. It's just a number, flow rate or pressure or whatever, right? And then it's up to the individual sensor and its interface on how to connect to the PLC, right? Is it a simple analog reference, which it might be just like a single wire with an analog voltage on it? Is it talking UART, you know, actual human readable data that it just spits out every second? And that happens pretty often too. Okay, it's up to you guys to take that data out of that device and get it into the program. All right, just a couple more that are really common that I want to go through. One that introduces the idea of a chemical sensor. Okay, very, 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 very often. All of the sensor is two electrodes, something that gives a lot of surface area, something that's easy to solder to, and then some kind of special substrate that's like treated with weird black magic to make it sensitive to whatever you want to read. In this case, if you guys have ever seen a ELT240 humidity sensor, temperature and humidity sensor, it has a moisture sensitive substrate. Okay, so the more moist that little piece of paper is in between those two pads, the more voltage actually, or sorry, it actually is a small computer on here, so it digitizes that data, it queries the sensor, digitizes the data, and reports it on this pin that we can read with an Arduino or a PLC or whatever. There's also a small digital temperature sensor on there too. Alcohol sensors work in a very similar way, except with a twist, they have to be hot in order to work. Okay, so they have a very, very small heating element inside of them. This is actually a ceramic heating element, and each of these legs either connects to the sensing element or a very small heater, right, a little coil that's inside here. So it brings it up to pretty high above ambient temperature. I think it's around like 100 degrees. Takes a reading and then powers down the sensor again. That's a cool, next time it comes up, it takes the sensor reading and then goes back down. So that's how low cost, you know, cost effective alcohol sensors work. And ethanol, hydrogen, lots of like combustible gas sensors work this way with this kind of special membrane. Yeah, I think that's about it for that one. We talked a little bit about ultrasonic sensing. Ultrasonic is great for flow rates. It's great for object detection, right? When detecting an object without actually touching it. Speed sensing as well. Oh, nice. So here is that example that I was talking about for, instead of a flow sensor, this is a density sensor. So we have sludge through a pipe, right? And essentially how much ultrasound is absorbed or reflected by that sludge would vary with density, it would vary with flow rate. And we would have a specific sensor that would report that data to us. Okay. Also used a lot in leak sensing for very, very small amounts of fluid flow for ultrasonic. Optical brake, we've already talked about, very easy, digital on and off, right? Very often just a digital output, high-low. Colorimetry is, I think this is just leading into AI, yeah. So a sensor really can just essentially be a black box with a data output, right, and ground. So if you have a black box, we power that black box. We have a data line that goes into our PLC. And that black box reports something. It can report like, is it the correct color? Is it the correct size? Is it the correct place? Whatever. But sometimes, more and more frequently in industry, that is actually an AI or computer vision component, right? It's a check on the line that, is this thing okay or not? You know, green light, red light, literally digital on, digital off, but the process itself could be incredibly complex and involved, right? Where there is an entire AI model, or you know, maybe we're making a call to the cloud or waiting for a response from a computer to weigh in that could feed back to our PLC and with just a simple flag, yes, no, we could include that in our system. Yeah.
Is it now typically AI, or is it like it takes the picture with the vision and it like has the parts in a set parameter? Like it's like the parts out of place, it knows without AI?
It really depends on the thing. Super specific. For example, circuit boards are frequently more done with AI. They used to be really manual, where it would like take 30 pictures, it would like fly through, and then a human would be presented with those 30 pictures. And then they would click through, and then they would hit the button that goes yes, then go back to the PLC and go that. But then they're closing the loop with like AI or just like simple, really rigidly programmed computer vision, right? Like check if this pixel is silver. If it's not, it means something's not soldered and we should kick it off the line. It can be that simple too. Yeah. Good question. Anyone else? Any other questions? Okay. So just a couple more that are really good to know. Again, this one, ubiquitous. It's in every bathroom, every airport, right? The automatic soap dispensers, you probably use this technology as the IR temperature sensor, or the IR sensor. Okay. So the way IR sensors work, the simplest ones that are often used for education, even still end up, in faucets and the like. Okay, they work by having two diodes. One is an emitter diode, and one is a receiver diode. They both look like LEDs, but essentially one detects how much infrared light there is, and one emits that same light, okay? And they actually do so in pulses, in slices of time, okay? So for 1/100th of a second, this light will turn on, it'll blink on, illuminating this light here, right? And that light will be received, again, they will only look during this same 1/100th of a second. It's like a blink. It's like I light up the light and I look for that light and then I don't care otherwise. Okay? It sees how much light was received from that spotlight and then gives a percent accordingly of that maximum. Okay, say I saw 50% of the maximum that I expect to ever see, right? If you held like a super white piece of paper against here that was ultra reflective and 100% of the light from his went into that would be 100%, right? So using this, we can have a very simple distance sensor, assuming something is moderately the same color, right? If we have an object here that is mildly reflective to infrared, which most things are, regardless of color, okay? We're in the infrared band here. If something is here, we will receive 25% of the light back. If something is here, we'll get 50%, right? Eliminate that. Here we'll get 75%, something coarse like that. Okay, so you guys have seen here that we made a really simple distance sensor. We can tell if something is this far, this far, this far, or this far, right? Or nothing's there at all. Okay, effectively, you guys can probably pretty easily see how you could make a soap dispenser or something that would trigger with this. Okay. The interesting part though is that this is an analog design. When you stick your hand underneath this device, it becomes a data analysis problem. The actual data that comes out of that device looks like this. Right? So what would seem to be a simple problem, a simple technology, actually becomes, what do you do with this data? This is now inside of your PLC. It's just a one-dimensional, right? If we're getting this with an analog input, we are digitizing this over time, just over and over and over again, seeing what it is at a simple given moment. What do we do with this data? That's kind of what I'm trying to teach you guys in this class too. Get an intuition about, right? There's a couple techniques that we've already talked about that you could use, right? The most simple one is a simple threshold. If IR val over threshold val, turn on the faucet, right? But we've talked about ways that this can go wrong, right? If you have noisy data, you might want to add hysteresis, right? You might want to do like a peak detector or something. You could do a set reset logic, you know, so you don't trigger the thing all the time. Okay, this is kind of where transducers end and logic begins. Okay, that again, the sensor is just giving us data, raw information, but it's still sometimes in unuseful forms or like one-dimensional, just like constantly updating. We still have to do something with that info, something meaningful with it anyway. Okay. So small tangent there. I hope it was still useful. Back to the actual sensor itself. IR sensors can be used in two different ways, essentially. Well, many different ways, but one of which is without this sending element. Okay. If we just have the receiving element, that's how we get things like IR temperature guns, right? That check how much light is being emitted by your forehead in the IR band. If you guys didn't know, it's something called black body radiation. If something was in the middle of space, okay, it would still give out photons, right? If it had some amount of heat to it in the IR band, okay? This is effectively what this IR sensor is reading all the time. Okay, it only cares about the photons that are given off as heat. Okay, so the amount, right, if we are seeing 1 photon per second or 3 photons per second, it's proportional to the amount of heat coming off of that object. And if we control the surface of that object, is it really matte, really rough and black? Or is it really shiny and white? It's called the R value of that object, right? This is kind of like typically 0.95. If we have a known object and we're pointing a sensor at that object, we can pretty much know what temperature it is based on how many photons we're seeing from the sensor. Hope that makes sense. Okay. All right, and the other one, like I said, we intentionally create IR and see how much IR we receive. The reason we do this time gating technique, right, where we kind of pulse it and only look during that pulse, is because things are giving off IR all the time. Okay, this signal that I was talking about here, if we didn't pulse it, looks like this. Let me know if you guys can't see this. Okay, so do you guys see all of this dead band information? Our actual signal is just this tiny little part. This is the only part that actually changes, like barely any at all, right? It's because all of this is all of the background IR junk, the light that it's seeing all the time, things giving off radiation or whatever. We're not controlling for ambient conditions. This is also what a pressure sensor would look like if you didn't kill off the ambient part, right? We would have a huge pressure signal, right, compared to absolute vacuum or whatever, and then the actual signal would only change a little bit on top of that. Okay, so some data processing glimpse for you guys, but I just want to make this clear that this is why we use this time gating technique, why we use differential techniques, reference values. All this stuff is to cut down on the amount of junk in our signal and maximize the dynamic, interesting part. Okay. All right, any questions before I keep moving? We're almost done with the sensors, I promise. Okay. All right, this is actually the last one. Talk about it real quickly. This is how a PM2.5 sensor works. You guys have ever seen environmental sensing or environmental reporting? Okay, there is very often a metric called PM2.5. What this means is particulate matter of the size approximately 2.5 micrometers. Okay, this is an interesting size. We actually monitor other ones like 0.1 and 1 micrometers. But 2.5 is interesting because this is the particle size that messes with people's lungs. Okay, asthmatics, pollen, particulates caused by manufacturing processes, dust, they all kind of fall in the range of approximately 2.5 micrometers. Okay, so it is relevant to us to make a device that can measure this, right? Can measure how many particles are in the air. Again, for if we're kicking up dust from contracting work, if we're creating weird chemicals from manufacturing processes, we want to make sure our air is safe. The way that we do that is by actually running those particles through a laser. Pretty cool. If we force those particles through an air channel, okay, they all kind of flow into here. This is just sampled air. We have a little pump that draws and pushes air through here, a little fan, right, that pushes it through. If we make it run through a super skinny channel and then shine a laser through that channel, we will get a little shadow puppet show of the particles that run through. The laser will actually briefly be blocked by the particles, and we will see again a one-dimensional graph. Kind of, well, it would be inverse actually. We go light, high laser, and then as particles pass it, we would get these little peaks, just like so. You count the peaks, you count the particles, you count the depth of the peak, the darkness, you count the particle size. You can kind of start to differentiate the size. Okay, so that's essentially, in a nutshell, how particle detection monitors work. So they have an air inlet, a sampling pump. Sometimes they have filters to make sure that you're only sampling approximately this range, or to kick out things greater or lesser than it. Again, reduce false positives. You have a photodiode or a laser that puts a spotlight on that little dust that literally magnified, suspended in the air, and then this spot will darken as something passes over it. There's a computer inside of here that counts these pulses, or has its own algorithm that can turn these pulses into a simple UART data line that says, some number. Typically that would be like 250 or 50 or whatever particles per second, say. And then you map that to air quality and health hazards and all that stuff. But the device would just be a small device with a little fan, right? And then it would have a small connector on it. That connector, again, would have like 12 volts, ground, and then a data line that would go into your PLC. And then that data line would, probably call a UART. If they would have another data line, that would be I2C, that more SPI, and so on. Right, that's how you actually get the data out of there. Okay, is that interesting? Does it make sense? Yeah, cool. Take that. All right. So that is the end of my sensor lecture. Any questions on that or transducers? Very good. Okay. All right. So I'm going to break this one up again. I'm not going to go through the whole lecture. I'm going to give you guys a lot of lap time today. We're going to go through IoT system architecture a little bit. Okay, so there's a lot of decisions that you guys have to make as program designers, right? We're kind of talking programming a little bit. Part of it is the mini of it all, right? Like faced against the bark of the tree, talking about data processing algorithms, right? Like really nose to the problem. How do we get a PLC to do the thing? Okay, but beyond that is how does the PLC fit into the greater scheme of things in our system? Okay, so we might be in a factory filled with other PLCs. One PLC might talk to many sensors, or each PLC might talk to one sensor, and there's like a master PLC that's conducting it all, right? Oftentimes it's up to possibly you guys to make that call. How many sensors go to which PLC, where do you install those PLCs, which talk to which and how, right? Has to be decided. And that's kind of what this gets into, as we call it system architecture. The great thing about modern PLCs is that it's fairly easy to get them to talk to each other. Literally, they have Ethernet ports in them, right? You can get them all on the same network, all talking to each other through Modbus, through that port, or they can all join through with these 3 wires. Again, those 3 wires get you on the Modbus bus, okay? And that allows communication between up to 255 different devices that are all sharing those 3 wires. And that's really just as simple as that. If we make good time, we'll go into a little bit of that, where we get PLCs on one group to talk to PLCs of another group. We'll see if we can get around to that. But the idea being that you would have the flexibility to decide best, like I said, if a one PLC with many sensors or many PLCs with one sensor is appropriate. Okay. Do I want to talk networking? I don't. Want to talk packet processing? I don't. Okay, well, let's talk a little bit about server architecture. All right, so at some point, we really become most concerned with data flow. Okay, right? Like, even when it comes to transducing, we're very preoccupied with the idea of getting this data. I keep getting bad markers. Sorry. Right, so we have our sensor, and then we have our PLC. Okay, then we probably have like a monitor, maybe some gauges. GAUGs. And then we probably have the cloud. Okay, so we have, actually even probably from like the real world. Okay, so we have here the real world piece of data that we're interested in, say pressure in a canister. Okay, we are very preoccupied with getting the pressure. Okay, this pressure is probably like an analog voltage. Right? So it starts out, the physical property is like voltage. Okay? Gets into our sensor. Now we might be talking a higher profile language like I2C, digital. Goes into our PLC. Now we have to communicate to our monitor, to our user, via a UI. Right? That pressure. We have to push that to gauges. And then we have to kick that data up to the cloud. Okay, so that data from the real world into the sensor, into the PLC, into the computer, and all the way up to the cloud has to be handled in every one of those bounces. Okay, from one device to another, that handoff has to be made. Once it's in the cloud, okay, that data gets bounced around even more. Okay, because again, pull back the curtain, the cloud is just more computers and trench coats, all doing different things. Okay, that sensor information is very often pushed up to a database where it's stored, right, into logs. This sensor information was received at this time from this sensor at this place, yada 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 yada. That's stuck in the database. Okay, goes right in the database. We also have some cloud provider. Okay, this is Microsoft, AWS, right, Google. Okay, these are the guys that are running the computers that access this database. Because whenever you go, hey, what's the current sensor temperature, or give me a plot of the previous hour of pressure sensoring, what you're actually doing is saying, hey server, give me all of the logs that match this time frame and display them. Okay, so this becomes a whole thing, IoT system architecture and design and programming. Okay, but that data is still getting bounced around, right? So it goes from our sensor, goes into the database, into the server, and then gets served back to our client. Okay, it really is the name of the game for a lot of things. Because what's the point in all this? really often, this pressure, right, to read on that tank is because some guy wants to see a gauge on a monitor, right? That it's green or red, that it's healthy or sick, that something needs to be done or not. Okay. And all of this programming, hardware setup is just to facilitate that, right? To have the process run as well as it could, and to keep an eye on it, keep tabs on it, even from afar. Again, the point of all this particular slide is not to make you guys IoT system architects overnight. It's to make you masters of the craft, but just to peel back the curtain just a little bit, right? Get you guys knowing these terms, not having you hear them from the first time thereafter, okay? So if any of this is interesting to you, highly suggest checking it out. IoT cloud architecture, okay? Useful to know. But sometimes this is really all we need to know, that there's some guy on your team that's going to handle this point. He'll give you a target that you point your PLC at, and that's kind of it. And then just all the data will flow up from there. They'll tell you how, make it work. But you would most often be preoccupied with getting a pressure sensor into your PLC and then working with the team from there. But if you can do that, then you're sitting pretty. Okay. IoT network.
Is that what it was?
Internet of Things is IoT. Yeah, sorry, I didn't actually define that. I don't know if I mentioned it too, but that was my job for a while, was IoT. I worked at an IoT company. I was a design engineer, so I would make gadgets that would do the sensing, that would attach to a PLC in a warehouse somewhere. That they already had a PLC, they needed to sense a particular thing. I would make a sensor that would be compatible with their system, that would talk to their cloud, visualize their whatever, and help them do that. So if you guys have any questions about that, let me know. But yeah.
I have a question.
Yeah.
Does someone create the interface system
Mm-hmm.
for the monitor?
Oh yeah. Yeah. So
Do we have to deal with some stuff like that?
in this class.
I mean, in the work environment.
Sure. Yeah. Very often they'll kind of want the whole thing. They'll be like, we have a sensor, we have a PLC, how do I get something on my monitor that does the thing? And then there will be a programming language that would work best to do that. So Node-RED, for example, is one of the languages. It's a visual language, so it's really good at making UIs with and plugging in data with. There's another thing that's called LabVIEW. I'll actually show you guys this. LabVIEW is crazy because it's a programming language that allows you to program in gauges and elements and stuff, where you can take a PLC-like device, it's a Texas Instruments thing, and then really quickly get it up on a UI. And then there's other industry-related things that are like this, but visual programming language or dashboard creator, they're often called. So actually, for this side, right, for the IoT stuff, so even at my company, I was the hardware guy, and then I worked with the software team. And then the software team was actually two teams in a trench coat, where it was the back-end guys, that did the hardcore database programming, data flow, talking different servers, talking to each other. And then there were the front-end guys. What color is the web page? Where does the icon go? How do the graphs look? Is it responsive with the web page when you resize the window? Yeah, that was their job, was to make it pretty, essentially. And then they had a separate team that they went here's where this data is going to go, and where this bar graph's going to be, and this histogram, and all that stuff. Any other questions? Okay. Cool stuff. Like it. I have this here. Just again, my intent is to peel back as many technological veils as possible. We are sitting on enormous levels of complexity all the time, right? Giants on the shoulders of giants with these things. But it's good to remember that this complexity is hidden from us, but it's always there, and it's worth knowing about. So if it interests you at all, you know, Google Network Stack, put it into TikTok, YouTube Shorts, whatever. Learn about it. Learn what a data packet that goes through an Ethernet cable consists of, okay, because it's actually pretty cool. I could go on about this for another 10 minutes, but I won't. I'll leave that for an instrument for you guys. Okay. It's very cool, very interesting. Okay, I'm gonna save this for later. That's all I'm gonna lecture you guys on for now. But for now, I'm gonna turn you guys loose to finish the existing labs, and I'll also host the new lab for those of you who are ready for it. Sound good? Okay, all right. Best of luck. Let me know if you need help.